Hello, and welcome back to the Sleep Lab, where we journey through the most profound mysteries of science and space to help you drift into peaceful slumber. I'm your guide through the cosmos tonight, and if you're new here, make sure to hit that subscribe button and ring the notification bell so you never miss our latest documentary adventures. If you enjoyed our previous explorations of black holes, distant galaxies, and the wonders of the universe, please take a moment to give this video a like and share it with fellow dreamers and science lovers who might enjoy this cosmic journey. Tonight, we're embarking on perhaps our most extraordinary voyage yet. In the infinite darkness, 124 light-years from Earth, in the constellation Leo, something extraordinary pulses through the cosmic void with a rhythm that might be the heartbeat of life itself. On a world 2.6 times the radius of Earth and 8 times more massive than our own, floating in the perfect zone around its gentle red dwarf star, Professor Nikku Madhusudhan's team at Cambridge University has detected something that has electrified the scientific community and divided opinion across the globe. Using the James Webb Space Telescope, researchers have identified chemical markers in K2-18b's atmosphere that suggest the presence of dimethyl sulfide, a molecule that on our planet is produced exclusively by living organisms, by marine phytoplankton and microscopic bacteria that have been writing the story of life in our oceans for billions of years. The concentrations detected are 20 times higher than anything we see on Earth, leading Professor Madhusudhan to declare this the strongest evidence, yet there is possibly life out there. Though other scientists urge caution, and NASA's recent studies have raised questions about these findings, the possibility remains tantalizing. So settle in. Let the gentle rhythm of scientific wonder carry you through the stars as we uncover the mystery of K2-18b, the world that might harbor our first cosmic neighbors. And if you find yourself drifting off during our journey, know that's exactly what we hope for here at the Sleep Lab. Let's move to our first part of the documentary, where we begin to unravel the extraordinary tale of a world that might be harboring life itself. In the infinite expanse of space, floating in the constellation Leo, K2-18b orbits its parent star with a measured rhythm that has captured the imagination of astronomers worldwide. This exoplanet, discovered by NASA's Kepler Space Telescope in 2015, initially appeared to be just another entry in the ever-growing catalog of distant worlds. But as we've learned time and again in astronomy, first impressions can be deceiving, and sometimes the most profound discoveries hide within the most seemingly ordinary observations. K2-18b sits approximately 124 light-years from Earth, a distance so vast that even traveling at the speed of light, a journey there would take longer than the entire recorded history of human civilization. To put this in perspective, if we were to send a message to any potential inhabitants of this world today, they would receive it in the year 2149, assuming they possess the technology and consciousness to decode our transmission. This exoplanet belongs to a category of worlds that doesn't exist in our own solar system, known as sub-Neptunes, positioned in that curious middle ground between rocky Earth-sized planets and the gas giants like Neptune and Uranus. With a radius 2.6 times that of Earth and a mass 8.6 times greater, K2-18b represents a type of planet that appears to be among the most common in our galaxy, yet remains completely absent from our own cosmic neighborhood. The planet orbits its host star, a red dwarf designated K2-18, every 33 Earth days, residing comfortably within what astronomers call the habitable zone or Goldilocks zone, that perfect distance where temperatures allow liquid water to exist on a planetary surface. Red dwarfs, like K2-18, burn their nuclear fuel so slowly and steadily that they can maintain consistent energy output for trillions of years, far longer than our own sun's projected lifespan of 10 billion years. This longevity provides an almost unimaginable amount of time for life to emerge, evolve, and potentially develop into complex forms. The story of K2-18b's rise to fame began with the Hubble Space Telescope's observations in 2019, when astronomers detected water vapor in the planet's atmosphere, marking it as one of the first sub-Neptunes confirmed to harbor this essential ingredient for life as we know it. But it wasn't until the James Webb Space Telescope turned its unprecedented infrared vision toward this distant world that the plot truly thickened. Webb's observations revealed a complex atmospheric composition that told a story far more intriguing than anyone had initially imagined. The telescope detected not just water vapor, but also methane and carbon dioxide, creating an atmospheric cocktail that suggested this world might be what researchers call a Hycean planet, a revolutionary concept proposed by Professor Nikku Madhusudhan and his team at Cambridge University. The Hycean world hypothesis represents a paradigm shift in our understanding of potentially habitable planets. Traditional thinking had focused almost exclusively on Earth-like rocky planets with thin atmospheres, but the Hycean model suggests that planets with thick hydrogen atmospheres overlying vast global oceans might actually be more conducive to life, and certainly more abundant in our galaxy. These worlds would feature atmospheric pressures and temperatures that could maintain liquid water oceans beneath their hydrogen-rich atmospheres, creating vast underwater realms that might harbor life in forms we're only beginning to imagine. The beauty of this concept lies in its expansion of the habitable real estate in our universe, suggesting that life might be thriving in environments we had never seriously considered. As Webb continued its observations of K2-18b, the atmospheric profile became increasingly fascinating. The presence of methane was particularly intriguing, as this molecule can be produced both by geological processes and by living organisms, making it what scientists call a potential biosignature when found in the right context. On Earth, methane in our atmosphere comes from a variety of sources, including volcanic activity, but also from countless microorganisms that have been producing this gas for billions of years. The detection of methane on K2-18b, combined with water vapor and carbon dioxide, painted a picture of a world with an active, dynamic atmosphere that could potentially support the complex chemistry required for life. But the real excitement came when researchers began analyzing Webb's most sensitive spectroscopic data from K2-18b's atmosphere. Using the telescope's advanced instruments, particularly the near-infrared spectrograph and the mid-infrared instrument, scientists could dissect the atmospheric composition with unprecedented precision, looking for the faint spectral fingerprints of molecules that might indicate biological processes. The process involves analyzing starlight as it filters through K2-18b's atmosphere during transit events, when the planet passes directly between its host star and Earth. During these transits, which occur every 33 days, different molecules in the planet's atmosphere absorb specific wavelengths of light, creating a unique spectral signature that can be decoded to reveal the atmospheric chemistry. It was during this meticulous analysis that Professor Madhusudhan's team made their most controversial discovery. Hidden within the spectral data was what appeared to be the signature of dimethyl sulfide, or DMS, a molecule that on Earth is produced exclusively by living organisms. Marine phytoplankton, the microscopic algae that drift through our oceans, release DMS as part of their metabolic processes, and this molecule plays a crucial role in cloud formation and climate regulation on our planet. The detection of DMS at concentrations 20 times higher than Earth's levels sent shockwaves through the scientific community, as there are no known geological processes that could produce this molecule in such abundance. If confirmed, this would represent the first detection of a molecule in an exoplanetary atmosphere that has no known non-biological source, making it potentially the most significant discovery in the search for extraterrestrial life. However, as with all groundbreaking scientific claims, the DMS detection has faced intense scrutiny from the global astronomical community. The statistical significance of the detection sits below the traditional 5 sigma threshold that physicists typically require for claiming a discovery, leading some researchers to urge caution in interpreting the results. Dr. Tessa Fisher from the University of Maryland bluntly stated that it's almost certainly not life, while other experts like Professor Catherine Hamans emphasize that extraordinary claims require extraordinary evidence. The debate has highlighted the challenges inherent in atmospheric spectroscopy at such vast distances, where even the most advanced instruments are pushed to their absolute limits. The controversy deepened when researchers discovered that DMS could potentially be produced through non-biological processes, particularly through interactions between stellar radiation and atmospheric chemistry that we don't fully understand. Additionally, the 2024 detection of DMS on comets in our own solar system provided another potential avenue for non-biological DMS production, though the concentrations observed on K2-18b far exceed anything seen in cometary environments. NASA's own follow-up studies in July 2025 concluded that there was no conclusive evidence for DMS in K2-18b's atmosphere, though they acknowledged that more observations would be needed to definitively resolve the question. Despite the scientific debate, the mere possibility that we might be detecting signs of life on a world 124 light-years away represents a moment of profound significance in human history. K2-18b has become more than just another exoplanet entry in astronomical databases. It has become a symbol of our expanding understanding of where life might exist in the universe and how we might detect it. The world continues to orbit its red dwarf star in peaceful regularity, completing each 33-day circuit, regardless of the intense scrutiny it now receives from Earth's most powerful telescopes, carrying its secrets in an atmosphere that may hold the answer to humanity's most fundamental question about our place in the cosmos. Let's move to our second part of the documentary, where we delve into the remarkable scientific journey that led to one of the most controversial discoveries in modern astronomy. In the quiet corridors of Cambridge University's Institute of Astronomy, Professor Nikku Madhusudhan has been quietly revolutionizing how we think about life in the universe. Born in India and educated at the prestigious Indian Institute of Technology before earning his PhD at MIT, Madhusudhan represents a new generation of astronomers who came of age during the golden era of exoplanet discovery. His career trajectory took him from the hallowed halls of MIT to Princeton, then Yale, before settling at Cambridge, where he now holds the prestigious title of Professor of Astrophysics and Exoplanetary Science. What makes Madhusudhan unique among his peers is not just his technical expertise in atmospheric modeling, but his willingness to challenge conventional wisdom about where and how life might exist in our galaxy. The concept that would eventually lead to the K2-18b Controversy began forming in Madhusudhan's mind years before the James Webb Space Telescope even launched. Traditional astrobiology had been laser-focused on finding Earth-like planets, rocky worlds with thin atmospheres orbiting sun-like stars at just the right distance to maintain liquid water on their surfaces. But Madhusudhan looked at the statistical reality of planetary systems discovered by Kepler and other surveys and realized that the most common type of planet in our galaxy wasn't Earth-like at all. Sub-Neptunes, worlds between the size of Earth and Neptune, appeared to dominate planetary systems throughout the cosmos, yet they were completely absent from our own solar system. This glaring absence meant that astronomers had no local laboratory to study these worlds, no nearby examples to guide their understanding of how such planets might work. It was this realization that led Madhusudhan to propose his groundbreaking Hycean world hypothesis. The term itself is a portmanteau of hydrogen and ocean, describing planets that might harbor vast liquid water oceans beneath thick hydrogen-rich atmospheres. Unlike the thin nitrogen-oxygen atmosphere of Earth, these worlds would be shrouded in dense blankets of hydrogen and helium, creating greenhouse conditions that could maintain liquid water at the surface, despite being much further from their host stars than traditional habitable zone models would suggest. The implications were staggering. If Hycean worlds could indeed support life, then the habitable real estate in our galaxy might be orders of magnitude larger than anyone had previously imagined. But proposing a revolutionary theory is one thing. Proving it is another entirely. Madhusudhan knew that the only way to test his Hycean hypothesis would be through detailed atmospheric observations of sub-Neptune exoplanets, observations that pushed existing telescope technology to its absolute limits. When the James Webb Space Telescope launched in late 2021, Madhusudhan saw his opportunity. Webb's unprecedented infrared sensitivity and spectroscopic capabilities would allow astronomers to dissect exoplanet atmospheres with a precision that had been unimaginable just a few years earlier. The telescope's revolutionary design, with its 6.5-meter segmented mirror and ultra-cold infrared instruments, could detect the faint spectral signatures of molecules in planetary atmospheres across interstellar distances. K2-18b became Madhusudhan's primary target for testing the Hycean hypothesis, and the results of his team's first observations in 2023 exceeded even his most optimistic expectations. Using Webb's near-infrared spectrograph and near-infrared imager and slitless spectrograph, the team detected not just water vapor, which had already been confirmed by Hubble, but also methane and carbon dioxide in concentrations that painted a picture of a world with a complex, active atmospheric chemistry. The presence of methane was particularly intriguing, as this molecule can be produced both by geological processes and by living organisms, making it a potential biosignature when found in the right atmospheric context. But it was the follow-up observations using Webb's mid-infrared instrument that would catapult K2-18b into the global spotlight and thrust Madhusudhan into the center of one of the most heated scientific debates of the decade. The MIRI observations covered a different wavelength range than the previous studies, providing what Madhusudhan described as an independent line of evidence, using a different instrument than we did before and a different wavelength range of light, where there is no overlap with the previous observations. When the data was processed and analyzed, the results sent shockwaves through the astronomical community. The spectral signature of dimethyl sulfide, a molecule that on Earth is produced exclusively by living organisms. The statistical significance of the detection reached what scientists call 3 sigma, meaning there was only a 0.3% chance that the signal was a random fluctuation in the data. While this falls short of the 5 sigma standard typically required for claiming a scientific discovery, it represents a level of confidence that cannot be easily dismissed. Madhusudhan, speaking from his laboratory at Cambridge's Institute of Astronomy, told reporters that this represented the strongest evidence yet there is possibly life out there, while acknowledging that more observations would be needed to reach the gold standard of statistical significance. The discovery process itself was a testament to the collaborative nature of modern astronomy. Madhusudhan's team included researchers from institutions around the world, each bringing specialized expertise to the complex task of atmospheric analysis. Co-author Mons Holmberg from the Space Telescope Science Institute in Baltimore described the moment of realization. It was an incredible realization, seeing the results emerge and remain consistent throughout the extensive, independent analyses and robustness tests. The team spent months verifying their results, running multiple independent analyses to ensure that the signal they were seeing was real and not an artifact of their data processing techniques. Yet even as Madhusudhan and his colleagues celebrated their breakthrough, they remained acutely aware of the extraordinary nature of their claims and the scrutiny that would inevitably follow. It is in no one's interest to claim prematurely that we have detected life, Madhusudhan cautioned, emphasizing the careful, methodical approach that would be required to confirm their findings. The professor understood that in the highly competitive and often contentious field of astrobiology, extraordinary claims require extraordinary evidence, and the burden of proof would be entirely on his team to demonstrate that their detection was both real and indicative of biological processes. The implications of Madhusudhan's work extend far beyond a single exoplanet. If K2-18b truly harbors life, it would validate his Hycean world hypothesis and suggest that life might be thriving on countless worlds throughout our galaxy that had previously been dismissed as uninhabitable. The professor's research represents a fundamental paradigm shift in how we approach the search for extraterrestrial life, moving away from the traditional focus on Earth-like worlds toward a more expansive view of habitability that encompasses the most common type of planet in our galaxy. As Madhusudhan himself noted, what we are seeing is a major paradigm shift in the field of exoplanet science. A shift that could redefine humanity's understanding of its place in the cosmic order. Standing in his laboratory, surrounded by the instruments and computers that process signals from distant worlds, Madhusudhan embodies the quiet determination of modern astronomical research. His work on K2-18b represents not just a potential discovery of life beyond Earth, but a new methodology for exploring the vast frontier of exoplanetary science, one atmospheric spectrum at a time. Let's move to our third part of the documentary, where we explore the fierce scientific debate that erupted following the announcement of dimethyl sulfide detection on K2-18b. In the quiet, methodical world of astronomical research, few discoveries have generated as much passionate disagreement as Professor Madhusudhan's claim of detecting potential biosignatures in a distant exoplanet's atmosphere. The announcement in April 2025 sent shockwaves through the global scientific community, creating a divide that illuminated both the promise and the peril of pushing observational astronomy to its absolute limits. What began as an exciting potential breakthrough quickly evolved into a complex debate about scientific methodology, statistical significance, and the extraordinary burden of proof required when claiming to have detected signs of life beyond Earth. The controversy centers on a fundamental question that strikes at the heart of astrobiology. What constitutes sufficient evidence for claiming the detection of life on another world? Professor Madhusudhan's team reported their findings with a 3 sigma statistical significance, meaning there was only a 0.3% probability that their detection occurred by random chance. In many fields of science, this would represent compelling evidence worthy of serious consideration. However, in the search for extraterrestrial life, where the implications of a positive detection are so profound, the scientific community typically demands 5 sigma significance, equivalent to a less than 0.00006% probability of chance occurrence. This higher standard exists because the consequences of false positives in astrobiology are so significant that extraordinary caution becomes not just advisable, but essential. Dr. Edward Schwieterman at the University of California, Riverside, emerged as one of the most vocal skeptics of the K2-18b findings, expressing deep concerns about both the statistical robustness of the detection and the methodology used to analyze the data. Schwieterman, an established astrobiologist with extensive experience in atmospheric modeling, pointed to 2 critical flaws in the Cambridge team's approach. First, he questioned whether the signal attributed to dimethyl sulfide was actually real, suggesting that the detection might be an artifact of data processing rather than a genuine atmospheric signature. Second, even if the signal was real, Schwieterman argued that there were plausible, non-biological explanations for DMS production that had not been adequately considered. The debate intensified when Dr. Ryan McDonald from the University of Michigan weighed in with his own analysis of the JWST data. McDonald, who specializes in exoplanet atmospheric analysis, explained that he had previously found molecular signatures at similar confidence levels that completely vanish when the same data is processed using different analytical models. His comments highlighted a critical vulnerability in cutting-edge astronomical research. The outcomes of spectroscopic analysis can change dramatically depending on the fine minutiae of how you treat the data, making it essential to use multiple independent analytical approaches to verify any claimed detection. McDonald's perspective reflected a broader concern among astronomers that the unprecedented quality of JWST data was outpacing the community's ability to develop robust analytical frameworks for interpreting it. NASA's response to the K2-18b controversy was notably measured and cautious. Unlike many other JWST discoveries, the space agency did not issue a press release celebrating Madhusudhan's findings, instead releasing a carefully worded statement on April 18, 2025, that emphasized the high evidentiary bar required for claiming biosignature detections. The statement read, "We would need follow-up studies and multiple converging lines of evidence to confirm true biosignatures and rule out false positives, possibly including independent data from multiple missions and extensive atmospheric modeling." This official response reflected NASA's institutional memory of previous controversies in astrobiology, including the infamous 1996 claims of microbial life in Martian meteorite ALH 84001, which were later largely debunked. Perhaps the most damaging blow to the K2-18b life hypothesis came in July 2025, when a NASA-led research team published their own independent analysis of the same JWST data. Led by Dr. Renyu Hu at NASA's Jet Propulsion Laboratory, this study concluded that there was no conclusive evidence for dimethyl sulfide in K2-18b's atmosphere, directly contradicting Madhusudhan's findings. The NASA team's analysis suggested that the spectral features attributed to DMS could be better explained by other atmospheric components and instrumental noise, raising serious questions about the reliability of the original detection. More troublingly, their atmospheric models demonstrated that even if DMS were present, it could potentially be produced through abiotic chemical processes in K2-18b's unique atmospheric conditions. The scientific community's skepticism was further fueled by the discovery of DMS in unexpected places within our own solar system. In 2024, researchers detected dimethyl sulfide in cometary environments, demonstrating that this molecule could be produced through non-biological processes involving the interaction between solar radiation and simple organic compounds. This finding severely undermined one of the key assumptions underlying the K2-18b life hypothesis, that DMS was exclusively a biosignature molecule. If comets could produce DMS through purely chemical processes, then it became plausible that similar abiotic mechanisms might operate in the complex atmospheric chemistry of distant exoplanets. Dr. Tessa Fisher at the University of Maryland delivered perhaps the most blunt assessment of the K2-18b claims, stating categorically that it's almost certainly not life. Fisher's dismissal reflected a broader concern among atmospheric scientists that the Cambridge team had not adequately considered alternative explanations for their observations. She pointed to laboratory experiments demonstrating that DMS could be synthesized through various non-biological pathways, particularly in the reducing atmospheric conditions that might exist on hydrogen-rich worlds like K2-18b. The criticism stung, particularly because it came from researchers who were generally supportive of the search for extraterrestrial life, but demanded rigorous standards of evidence. The controversy also highlighted fundamental differences in scientific philosophy between different research groups. Madhusudhan and his colleagues argued that their detection represented the beginning of a scientific conversation rather than a definitive claim, emphasizing that they had explicitly called for additional observations to confirm or refute their findings. They pointed out that the detection was made using multiple independent instruments on JWST, including NIRIS, NIR SPEC, and MIRI, providing what they considered convergent lines of evidence. The fact that the signal appeared across different wavelength ranges and different observing modes, they argued, made it less likely to be an instrumental artifact or data processing error. However, critics countered that the use of multiple instruments did not necessarily validate the detection, if all the instruments were subject to similar systematic uncertainties, or if the analytical methods used to process the data contained similar assumptions. Dr. Sarah Hurst, a planetary scientist at Johns Hopkins University, emphasized that laboratory studies had clearly demonstrated multiple pathways for abiotic DMS production, making it premature to invoke biological explanations for any DMS detected in exoplanetary atmospheres. Her comments reflected a fundamental principle in astrobiology known as the extraordinary claims require extraordinary evidence standard, originally articulated by Carl Sagan in the context of SETI research. The debate over K2-18b also revealed tensions within the astronomical community about the pace of discovery announcements and the role of media attention in scientific research. Some researchers criticized the Cambridge team for publicizing their findings before the broader community had time to independently verify the results, arguing that premature announcements could damage public trust in science if the claims were later retracted. Others defended the team's right to publish their findings and engage with the media, pointing out that peer review and scientific debate were healthy parts of the research process. As the controversy continued to unfold throughout 2025, it became clear that resolving the K2-18b question would require not just additional observations, but also fundamental advances in our understanding of exoplanetary atmospheric chemistry and our analytical techniques for processing JWST data. The debate serves as a sobering reminder that even with the most advanced telescopes ever built, the search for life beyond Earth remains an extraordinarily challenging endeavor, where the line between groundbreaking discovery and analytical artifact can be razor thin. Let's move to our fourth part of the documentary, where we dive deep into the molecular detective story that lies at the heart of the K2-18b controversy and explore how scientists decipher the chemical secrets hidden in starlight. The search for life beyond Earth has always been fundamentally a search for chemistry, a quest to identify molecular signatures that could indicate biological processes operating in alien environments. On our own planet, dimethyl sulfide represents one of nature's most distinctive chemical calling cards, a molecule so intimately connected to life that its detection on another world would seem to provide compelling evidence for biology beyond Earth. Yet as the debate over K2-18b has revealed, the relationship between chemistry and biology becomes far more complex when we venture into the alien environments of distant exoplanets. Dimethyl sulfide, with its distinctive chemical formula C2H6S, is perhaps most familiar to us as the molecule responsible for the characteristic smell of ocean beaches and coastal environments. On Earth, this pungent compound is produced almost exclusively by marine phytoplankton, microscopic organisms that drift through our oceans in countless billions, conducting photosynthesis and forming the foundation of marine food webs. These tiny organisms release DMS as part of their metabolic processes, particularly when they are stressed or dying, creating a chemical signal that has been linked to cloud formation and climate regulation on a global scale. The molecule's presence in Earth's atmosphere is ephemeral, with a lifetime measured in days rather than years, which means that its continued detection requires constant replenishment by living organisms. This short atmospheric lifetime has made DMS particularly attractive to astrobiologists as a potential biosignature, since any significant accumulation of the molecule would seem to demand an active biological source. The theoretical foundation for using DMS as a biosignature rests on what scientists call the disequilibrium principle, the idea that life creates chemical imbalances in planetary atmospheres that would not exist in sterile environments. Living organisms consume certain molecules and produce others, creating atmospheric compositions that deviate dramatically from what we would expect from purely chemical and physical processes. On Earth, the most famous example of this principle is our oxygen-rich atmosphere, which exists only because billions of years of photosynthesis have pumped oxygen into our air at rates far exceeding its natural destruction through geological processes. Similarly, the presence of DMS in significant concentrations might indicate biological activity, since there are few known abiotic processes that could produce and maintain substantial amounts of this molecule in a planetary atmosphere. However, the K2-18b case has forced scientists to confront the limitations of this biosignature approach when applied to alien worlds with atmospheric conditions utterly unlike those on Earth. The planet's thick hydrogen atmosphere, with pressures potentially hundreds of times greater than Earth's surface pressure, creates a chemical environment where familiar assumptions about molecular behavior may no longer apply. Dr. Renyu Hu, from NASA's Jet Propulsion Laboratory, who led the team that challenged Madhusudhan's findings, emphasized that the chemical processes operating in K2-18b's atmosphere might be fundamentally different from anything we observe on Earth. His team's atmospheric models suggested that the interaction between hydrogen, water vapor, and trace sulfur compounds in K2-18b's dense atmosphere could potentially produce DMS through purely abiotic pathways, particularly if the planet's atmosphere experiences the kind of vertical mixing and temperature gradients that their models predicted. The controversy deepened significantly when astronomers began discovering DMS in environments where life was definitely not responsible for its production. In 2024, researchers detected dimethyl sulfide in cometary environments, demonstrating that the molecule could be synthesized through the interaction of simple organic compounds with solar radiation, completely independent of any biological processes. This discovery sent shockwaves through the astrobiology community because it undermined one of the fundamental assumptions underlying the use of DMS as a biosignature. If comets, which are essentially frozen chemical laboratories left over from the early solar system, could produce DMS through purely chemical processes, then it became plausible that similar mechanisms might operate in the complex atmospheric chemistry of exoplanets like K2-18b. The comet discovery also highlighted a broader challenge facing astrobiology: the difficulty of distinguishing between biological and non-biological sources of potentially interesting molecules when dealing with alien environments. Dr. Sarah Hurst at Johns Hopkins University pointed to laboratory experiments demonstrating multiple pathways for abiotic DMS production, particularly in reducing atmospheric conditions rich in hydrogen and simple organic compounds. These experiments showed that under the right conditions of temperature, pressure, and chemical composition, DMS could be synthesized through purely chemical reactions involving sulfur-bearing compounds and organic molecules without any involvement of living organisms. The statistical controversy surrounding the K2-18b detection reflects deeper questions about how we should interpret weak signals in astronomical data. The 3 sigma confidence level reported by Madhusudhan's team means that there is only a 0.3% probability that their detection occurred by random chance, which in many scientific contexts would represent compelling evidence. However, in the search for extraterrestrial life, where false positives can have profound implications for our understanding of our place in the universe, many researchers demand the 5 sigma standard typically used in particle physics, equivalent to a less than 0.00006% probability of chance occurrence. This higher standard exists because the consequences of incorrectly claiming the detection of life are so significant that extraordinary caution becomes not just advisable, but essential. The debate has also revealed the challenges inherent in analyzing JWST data, which provides unprecedented detail about exoplanetary atmospheres, but also pushes analytical techniques to their limits. Dr. Ryan McDonald from the University of Michigan described finding molecular signatures at similar confidence levels that completely vanish when the same data is processed using different analytical models, highlighting how the outcomes of spectroscopic analysis can depend critically on the fine minutiae of how you treat the data. This sensitivity to analytical choices reflects the fact that astronomers are still developing robust frameworks for interpreting the exquisitely detailed spectra that JWST can provide, particularly for complex atmospheric compositions that have no analogs in our solar system. The case of K2-18b has also forced scientists to confront the possibility that their Earth-centric assumptions about biosignatures might be fundamentally flawed when applied to alien worlds. The planet's classification as a potential Hycean world, with its hydrogen-rich atmosphere overlying a global ocean, represents an environment so different from Earth that our understanding of how chemistry and biology might interact becomes highly speculative. Even if DMS is being produced biologically on K2-18b, the organisms responsible might operate through metabolic pathways completely unknown on Earth, producing the molecule through biochemical processes that we cannot even imagine. Conversely, the unique atmospheric conditions on K2-18b might enable abiotic chemical processes that could mimic biological signatures in ways that we are only beginning to understand. Perhaps most importantly, the K2-18b controversy has highlighted the need for multiple, independent lines of evidence before claiming the detection of life on another world. NASA's cautious response to Madhusudhan's findings emphasized that we would need follow-up studies and multiple converging lines of evidence to confirm true biosignatures and rule out false positives, possibly including independent data from multiple missions and extensive atmospheric modeling. This approach reflects hard-learned lessons from previous controversies in astrobiology, including the famous 1996 claims of microbial life in Martian meteorite ALH 84001, which generated enormous excitement before being largely debunked by subsequent research. The molecular detective story of K2-18b continues to unfold as astronomers plan additional observations with JWST and other instruments. The planet remains one of the most intensively studied exoplanets in the sky, with multiple research teams collecting data and developing increasingly sophisticated models to understand its atmospheric chemistry. Whether K2-18b ultimately proves to harbor life or represents an exotic example of abiotic chemistry, the controversy has already advanced our understanding of how to search for life in the cosmos and highlighted both the promise and the perils of interpreting chemical signatures from distant worlds. Let's move to our 5th part of the documentary, where we explore the remarkable technological marvel that has made the K2-18b discovery possible and revolutionized our understanding of distant worlds. The James Webb Space Telescope represents humanity's most ambitious attempt to peer into the depths of space and time, a $10 billion testament to human ingenuity that floats in the darkness 1.5 million kilometers from Earth, at a gravitational balance point called L2, where the combined pull of Earth and Sun keeps it in perfect orbital harmony. This engineering masterpiece, decades in the making and launched on Christmas Day 2021, has already fundamentally transformed our approach to studying exoplanets, providing unprecedented insights into worlds that orbit distant stars across the galaxy. The telescope's revolutionary capabilities stem from its massive 6.5-meter segmented primary mirror, composed of 18 hexagonal gold-coated beryllium segments that work together as a single light-collecting surface, larger than any space telescope ever built. This mirror, nearly 3 times the size of Hubble's primary mirror, provides Webb with unprecedented light-gathering power that allows it to detect incredibly faint signals from distant exoplanets. But size alone doesn't explain Webb's transformative impact on exoplanet science. It's the telescope's specialized infrared instruments that have opened entirely new windows into the composition and characteristics of alien worlds. Operating in the mid and near-infrared wavelengths, Webb can detect the thermal emission from exoplanets themselves, as well as analyze the subtle changes in starlight that occur when these worlds pass in front of their host stars. The technological breakthrough that made the K2-18b atmospheric analysis possible lies in Webb's extraordinary spectroscopic capabilities, particularly through its near-infrared spectrograph, NIRSPEC, near-infrared imager, and slitless spectrograph, NIRISS, and mid-infrared instrument, MIRI. These instruments can dissect starlight into its component wavelengths with such precision that they can identify the chemical fingerprints of individual molecules in exoplanetary atmospheres across interstellar distances. When K2-18b transits in front of its host star every 33 days, these instruments capture the subtle changes in the star's spectrum caused by different molecules in the planet's atmosphere, absorbing specific wavelengths of light. The process requires extraordinary precision, as the atmospheric signal represents less than 0.01% of the total light from the star, demanding computational techniques and analytical methods that push the boundaries of what's possible with current technology. Webb's success in exoplanet discovery has extended far beyond the controversial K2-18b case, establishing a new paradigm for how we study distant worlds. In June 2025, the telescope achieved a historic milestone by directly imaging its first exoplanet, a Saturn-sized world designated TWA-7b that orbits within the debris disk of a young star 111 light-years away. This discovery marked a revolutionary advancement in exoplanet detection techniques, as direct imaging represents one of the most challenging approaches to finding alien worlds. The planet's star outshines it by a factor of 10 million, making detection possible only through the use of a sophisticated coronagraph that blocks the star's light while revealing the faint thermal emission from the planet itself. The French-developed coronagraph installed on Webb's MIRI instrument essentially creates an artificial eclipse, allowing astronomers to study objects that would otherwise be completely overwhelmed by their host star's brilliance. The TWA-7b discovery demonstrates Webb's potential to revolutionize our understanding of planetary system formation and evolution. Located roughly 52 times farther from its star than Earth is from the Sun, this Saturn mass world occupies a gap in the star's debris disk that was likely carved out by the planet's gravitational influence. Computer simulations conducted by the research team showed that a planet of this mass in this location would indeed create the exact ring structure observed in the system, providing compelling evidence that the detected object is indeed a planet rather than a background star or galaxy. The discovery represents a significant step toward the ultimate goal of directly imaging Earth-sized planets around nearby stars, bringing us closer to the possibility of studying potentially habitable worlds through direct observation rather than indirect detection methods. Beyond individual planet discoveries, Webb has also made significant contributions to our understanding of planetary systems within our own cosmic neighborhood. In August 2025, the telescope discovered compelling evidence for a giant planet orbiting Alpha Centauri A, the nearest sun-like star to our solar system at just over 4 light-years away. This potential discovery, if confirmed, would represent the closest known exoplanet to Earth and could provide unprecedented opportunities for detailed study of an alien world. The planet appears to be a gas giant approximately the mass of Saturn, orbiting in a highly elliptical path that brings it between 1 and 2 times the Earth-Sun distance from its host star. The discovery required meticulous observations using Webb's coronagraphic capabilities to block the brilliant light of Alpha Centauri A, revealing an object more than 10,000 times fainter than the star itself. The Alpha Centauri discovery also highlights both the power and the challenges of cutting-edge astronomical research. Initial observations in August 2024 clearly detected the candidate planet, but follow-up observations in February and April 2025 failed to detect it again, leading to what researchers dubbed the case of the disappearing planet. Computer simulations of millions of possible orbits suggest that the planet's highly elliptical path could explain its intermittent visibility, as certain portions of its orbit would bring it too close to the star to be detected by Webb's instruments. This discovery underscores the complexity of direct exoplanet detection and the need for sustained observational campaigns to confirm and characterize these distant worlds. Webb's capabilities have also extended to discoveries within our own solar system, demonstrating the telescope's versatility across a wide range of astronomical targets. In August 2025, astronomers using Webb discovered a previously unknown moon orbiting Uranus, designated S/2025 U1, which measures only about 6 miles in diameter and orbits roughly 35,000 miles from the planet's center. This tiny world, the 29th known moon of Uranus, was completely invisible to NASA's Voyager 2 probe during its 1986 flyby and remained undetected by other telescopes until Webb's extraordinary sensitivity revealed its presence. The discovery required 10 separate 40-minute exposures using Webb's near-infrared camera, demonstrating the telescope's ability to detect incredibly faint objects even within our own solar system. The technical achievements that enable Webb's groundbreaking discoveries rely on maintaining the telescope's instruments at temperatures near absolute zero, just 50 Kelvin above the coldest possible temperature. This extreme cooling is necessary because the telescope's infrared detectors would be overwhelmed by their own thermal emission if operated at higher temperatures. A massive sunshield, larger than a tennis court when deployed, provides the necessary protection from solar radiation, while passive cooling systems ensure that the instruments remain cold enough to detect the faint infrared signatures from distant worlds. The engineering challenges involved in deploying this sunshield and precisely aligning the segmented primary mirror represent some of the most complex operations ever attempted in space, requiring hundreds of individual mechanical deployments that had to work perfectly millions of kilometers from Earth. The data processing and analysis techniques developed for Webb represent another technological revolution in astronomy. The telescope generates enormous amounts of data during each observation, requiring sophisticated algorithms and computational methods to extract meaningful scientific information from the raw measurements. The spectroscopic analysis that revealed the potential dimethyl sulfide signature on K2-18b involved processing terabytes of data through complex atmospheric models that account for the three-dimensional structure of planetary atmospheres, the effects of stellar contamination, and the instrumental characteristics of Webb's detectors. These analytical challenges have driven the development of new statistical methods and machine learning approaches that are transforming how astronomers interpret observations across all areas of the field. As Webb continues its mission, with enough fuel to operate for at least 20 years, the telescope promises to revolutionize our understanding of exoplanets and their potential for harboring life. Future observations will target an increasingly diverse population of worlds, from hot Jupiters with atmospheres of vaporized metals to potentially habitable rocky planets around nearby red dwarf stars. The telescope's unprecedented capabilities have already demonstrated that the universe contains a stunning diversity of planetary environments, many of which challenge our preconceptions about how planets form and evolve, bringing us ever closer to answering the profound question of whether life exists beyond our solar system. Let's move to our sixth part of the documentary, where we journey through the remarkable discoveries that have emerged from the James Webb Space Telescope's revolutionary observations, painting a broader picture of how this technological marvel is reshaping our understanding of planetary systems across the cosmos. While the debate over K2-18b continues to unfold, Webb has quietly amassed an extraordinary catalog of exoplanet discoveries and observations that demonstrate the incredible diversity of worlds that exist beyond our solar system, each one challenging our preconceptions about how planets form, evolve, and potentially harbor life. These discoveries collectively represent a new chapter in humanity's quest to understand our place in the universe, revealing that the cosmos contains planetary environments far more varied and exotic than we ever imagined. The most groundbreaking of Webb's recent discoveries came in June 2025, when astronomers achieved something that had never been accomplished before: the direct imaging discovery of an entirely new exoplanet. The world, designated TWA-7b, represents a watershed moment in exoplanet science, as it marked the first time that Webb had independently discovered a planet through direct observation rather than indirect detection methods. Located 111 light-years away, in the constellation Centaurus, this Saturn-mass world orbits within the debris disk of a young star that is only 6.4 million years old, making it practically an infant by cosmic standards. The planet's discovery required the use of Webb's sophisticated coronagraphic capabilities, essentially creating an artificial eclipse that blocked the star's overwhelming brightness to reveal the faint thermal emission from the planet itself, which shines over 10,000 times fainter than its host star. What makes TWA-7b particularly significant is not just its discovery, but what it tells us about planetary formation in young stellar systems. The planet orbits approximately 52 times farther from its star than Earth orbits the Sun, residing within a complex system of debris rings that show clear evidence of gravitational sculpting by the planet's presence. Computer simulations conducted by the research team demonstrated that a Saturn-mass planet in this exact location would create the precise ring structure observed by Webb, providing compelling confirmation that the detected object is indeed a planet rather than a background galaxy or other astronomical phenomenon. The discovery validates theoretical predictions about how planets interact with debris disks during the early stages of stellar system formation, offering direct observational evidence for processes that were previously understood only through computer modeling. Perhaps even more remarkable than the K2-18b discovery is Webb's detection of what may be the closest exoplanet to Earth ever found through direct imaging. In August 2025, astronomers using Webb's mid-infrared instrument reported compelling evidence for a giant planet orbiting Alpha Centauri A, the nearest Sun-like star to our solar system at just 4.37 light-years away. This potential discovery, if confirmed, would represent the closest known exoplanet to Earth and could provide unprecedented opportunities for detailed characterization of an alien world. The candidate planet appears to be a gas giant with approximately Saturn's mass, orbiting its host star in a highly elliptical path that varies between 1 and 2 times the Earth-Sun distance. However, the Alpha Centauri discovery also illustrates the challenges and complexities of cutting-edge astronomical research. While initial observations in August 2024 clearly detected the candidate planet, follow-up observations in February and April 2025 failed to detect it again, leading researchers to dub it the case of the disappearing planet. Computer simulations of millions of possible orbital configurations suggest that the planet's highly elliptical orbit could explain this intermittent visibility, as certain portions of its path would bring it too close to the star to be detectable by Webb's instruments. Graduate student Aniket Sanghi at Caltech explained that in roughly half of the simulated orbits, the planet would move too close to Alpha Centauri A during February and April 2025 to be visible to Webb, providing a plausible explanation for the non-detections during those observing periods. The significance of a potential planet around Alpha Centauri A extends far beyond its proximity to Earth. The existence of a giant planet in such a close binary star system would challenge current theories of planetary formation and survival in chaotic gravitational environments. Alpha Centauri A and its companion star, Alpha Centauri B, orbit each other at distances comparable to those between our Sun and Neptune, creating a complex gravitational environment where planetary formation and long-term stability become highly problematic according to traditional models. If confirmed, this planet would represent the most similar world to our solar system's gas giants ever discovered, sharing similar temperature and age characteristics while existing in a stellar environment completely unlike our own. Webb's discoveries have also extended into our own solar system, demonstrating the telescope's incredible sensitivity across a wide range of astronomical targets. In August 2025, astronomers using Webb's near-infrared camera discovered a previously unknown moon orbiting Uranus, designated S/2025 U1, which measures only about 6 miles in diameter. This tiny world, now the 29th known moon of Uranus, was completely invisible to NASA's Voyager 2 probe during its historic 1986 flyby and remained undetected by subsequent observations until Webb's extraordinary capabilities revealed its presence. The discovery required 10 separate 40-minute exposures, demonstrating the telescope's ability to detect incredibly faint objects even within our own planetary neighborhood. The Uranus Moon discovery provides important insights into the complex dynamics of the outer solar system and the formation history of the ice giant planets. S/2025 U1 orbits approximately 35,000 miles from Uranus's center on a nearly circular path, suggesting that it formed in its current location rather than being a captured asteroid or comet. The Moon joins a family of small satellites that orbit between Uranus's ring system and its 5 major moons, occupying a dynamically active region where gravitational interactions between the planet, its rings, and multiple moons create complex orbital mechanics that are still not fully understood. These individual discoveries represent just the beginning of Webb's transformative impact on exoplanet science. The telescope's unprecedented infrared sensitivity and spectroscopic capabilities have opened entirely new avenues for studying alien worlds, from characterizing the atmospheric composition of gas giants to detecting the thermal emission from potentially rocky planets around nearby stars. Each observation pushes the boundaries of what's possible with current technology, while simultaneously revealing new questions about planetary formation, evolution, and the potential for habitability in diverse cosmic environments. The success of Webb's direct imaging capabilities also points toward future possibilities for detecting and studying potentially habitable worlds. The French-developed coronagraph that enabled the TWA-18b discovery represents just the first generation of instruments designed to block starlight and reveal orbiting planets. Future space-based telescopes will carry even more sophisticated coronagraphs capable of detecting planets with masses as low as 10% of Jupiter's, bringing us progressively closer to the ultimate goal of directly imaging Earth-sized worlds around nearby stars. The techniques and methodologies developed through Webb's current observations are laying the groundwork for future missions specifically designed to search for biosignatures in the atmospheres of potentially habitable exoplanets. As Webb continues its mission with enough fuel to operate for at least 2 decades, the telescope promises to revolutionize our understanding of planetary systems and their potential for harboring life. The diversity of worlds already discovered through Webb's observations suggests that the universe contains planetary environments spanning an incredible range of masses, compositions, and orbital configurations, many of which have no analogs in our own solar system. From the controversial potential biosignatures on K2-18b to the direct imaging of young giant planets and the discovery of tiny moons in our cosmic backyard, Webb is providing humanity with its first comprehensive view of the true complexity and wonder of planetary systems throughout our galaxy, bringing us ever closer to answering the fundamental question of whether we are alone in the universe. Let's move to our 7th part of the documentary, where we explore the profound implications of Webb's discoveries for our understanding of planetary systems and examine how these findings are fundamentally reshaping our conception of how worlds form, survive, and potentially harbor life throughout the cosmos. The telescope's remarkable achievements represent more than just a series of individual discoveries. They constitute a revolutionary transformation in how we approach the study of exoplanets, revealing a universe filled with planetary environments that challenge our most basic assumptions about what constitutes a habitable world. Each observation by Webb pushes the boundaries of our knowledge further into uncharted territory, forcing astronomers to reconsider long-held theories about planetary formation, atmospheric evolution, and the conditions necessary for life to emerge and flourish. The discovery of TWA-7b through direct imaging represents a paradigm shift in exoplanet detection methodology that extends far beyond the achievement itself. This Saturn mass world, orbiting within the debris disk of its 6.4 million-year-old host star, demonstrates that planets can form and maintain stable orbits in environments previously thought to be too chaotic for planetary survival. The planet's location, approximately 52 times farther from its star than Earth, orbits the Sun, places it in a region where traditional planet formation models suggested that gravitational perturbations from the surrounding debris disk would prevent any planetary body from achieving a stable configuration. Yet TWA-7b not only exists, but appears to be gravitationally sculpting the very debris disk that surrounds it, creating the narrow ring structure observed by Webb through a process that validates decades of theoretical predictions about planet-disk interactions. The implications of finding a Saturn-mass planet through direct imaging extend into future observational strategies and technological development. TWA-7b is 10 times lighter than any previously imaged exoplanet, marking a significant step toward the ultimate goal of directly detecting Earth-sized worlds around nearby stars. The success of the French-developed coronagraph installed on Webb's MIRI instrument proves that current technology can overcome the enormous brightness difference between stars and their planetary companions, at least for planets orbiting at relatively large distances from their host stars. This technological validation provides the foundation for even more ambitious direct imaging projects, with scientists already planning observations of planets with masses as low as 10% of Jupiter's mass, bringing us progressively closer to detecting potentially habitable rocky worlds. The case of the potential planet around Alpha Centauri A illustrates both the extraordinary possibilities and the inherent challenges of pushing astronomical observations to their absolute limits. The disappearing planet phenomenon, where Webb detected a candidate planet in August 2024, but failed to observe it during follow-up observations in February and April 2025, highlights the complex orbital dynamics that can govern planetary systems in binary star environments. The computer simulations conducted by graduate student Aniket Sanghi and his colleagues at Caltech demonstrate that highly elliptical orbits could explain the intermittent visibility, with the planet moving too close to its host star during certain portions of its orbit to be detectable by Webb's instruments. This discovery process reveals the patience and persistence required for cutting-edge astronomical research, where definitive conclusions often require sustained observational campaigns spanning multiple years. If confirmed, the Alpha Centauri A planet would represent the closest exoplanet to Earth ever discovered through direct imaging, located just 4.37 light-years away in our nearest stellar neighbor system. The planet's estimated mass, approximately equivalent to Saturn's, and its orbital characteristics would make it remarkably similar to the giant planets in our own solar system, providing an unprecedented opportunity for comparative planetary science. However, its very existence in a close binary star system would fundamentally challenge current theories of planetary formation and long-term stability. Alpha Centauri A and B orbit each other at distances comparable to those between our Sun and Neptune, creating a gravitationally chaotic environment where traditional models suggest that planetary formation should be severely disrupted and long-term orbital stability nearly impossible to maintain. The discovery of the tiny moon S2025 U-1 orbiting Uranus demonstrates Webb's extraordinary sensitivity across a wide range of astronomical targets, from distant exoplanets to objects within our own solar system. This 6-mile diameter world, the 29th known moon of Uranus, remained completely invisible to NASA's Voyager 2 probe during its 1986 flyby and eluded detection by subsequent ground-based and space-based observations until Webb's unprecedented infrared capabilities revealed its presence. The moon's discovery required 10 separate 40-minute exposures using Webb's near-infrared camera, pushing the telescope's detection limits to reveal objects that would have been impossible to observe with previous generations of astronomical instruments. The orbital characteristics of S2025 U-1 provide important insights into the formation and evolution of the Uranian satellite system. Located approximately 35,000 miles from Uranus's center and following a nearly circular orbit, the moon appears to have formed in its current location rather than being a captured asteroid or comet. This formation scenario suggests that the ice giant planets possessed substantial debris disks during their formation phase, similar to those observed around young stars like TWA7, providing the raw material for small satellite formation even in the outer reaches of our solar system. The discovery also highlights the dynamic nature of planetary satellite systems, where gravitational interactions between planets, rings, and multiple moons create complex orbital mechanics that continue to evolve over cosmic timescales. Webb's discoveries collectively paint a picture of a universe where planetary systems exhibit far greater diversity and complexity than our solar system-centric models had predicted. The traditional approach to exoplanet science, which focused primarily on finding Earth-like worlds in Earth-like orbits around Sun-like stars, has given way to a more expansive understanding of habitability that encompasses a vast range of planetary masses, atmospheric compositions, and orbital configurations. The controversy surrounding K2-18b's potential biosignatures exemplifies this paradigm shift, as it involves a type of world, a sub-Neptune with a thick hydrogen atmosphere that doesn't exist anywhere in our solar system, yet appears to be among the most common types of planets in our galaxy. The technological achievements that enable Webb's groundbreaking observations represent the culmination of decades of engineering development and scientific innovation. The telescope's 6.5-meter segmented mirror, operating at temperatures just 50 Kelvin above absolute zero, provides light-gathering power and infrared sensitivity that exceeds anything previously achieved in space-based astronomy. The sophisticated coronagraphic techniques that enabled the direct detection of TWA7b required precise control of optical systems to block starlight while preserving the faint signals from orbiting planets, a technological challenge that pushes the boundaries of what's possible with current engineering capabilities. These achievements provide the foundation for even more ambitious future missions, including dedicated exoplanet imaging telescopes designed specifically to search for biosignatures in the atmospheres of potentially habitable worlds. The statistical and analytical challenges revealed by Webb's observations also highlight the need for new methodological approaches to interpreting astronomical data. The debate over K2-18b's dimethyl sulfide detection demonstrates how the unprecedented quality of Webb's spectra can reveal molecular signatures that push the limits of current analytical techniques, creating situations where different research groups can reach contradictory conclusions using the same observational data. This challenge has driven the development of new statistical methods and machine learning approaches that are transforming how astronomers extract scientific insights from complex data sets, establishing analytical frameworks that will be essential for interpreting observations from future generations of even more powerful telescopes. As Webb continues its mission, with enough fuel to operate for at least 2 decades, the telescope promises to revolutionize our understanding of planetary systems across the entire spectrum of cosmic environments. From the detection of potentially life-bearing molecules in exoplanetary atmospheres to the direct imaging of Earth-sized worlds around nearby stars, Webb's ongoing observations are providing humanity with its first comprehensive view of the true diversity and complexity of planets throughout our galaxy, fundamentally transforming our perspective on our place in the cosmic order and bringing us ever closer to answering the ultimate question of whether life exists beyond our solar system. Let's move to our 8th part of the documentary, where we contemplate the philosophical and existential implications of Webb's discoveries and examine how these findings are fundamentally altering humanity's understanding of our place in the cosmic order. The telescope's revolutionary observations have done more than simply catalog new worlds and atmospheric compositions. They have initiated a profound shift in how we conceptualize life, intelligence, and consciousness in the universe. Each discovery by Webb forces us to confront age-old questions about human uniqueness and cosmic significance, while simultaneously opening entirely new avenues of philosophical inquiry that our ancestors could never have imagined. The potential detection of biosignatures on K2-18b, the direct imaging of alien worlds, and the revelation of planetary diversity on an unprecedented scale all contribute to what may be the most significant paradigm shift in human thought since the Copernican revolution displaced Earth from the center of the universe. The controversy surrounding K2-18b's potential biosignatures represents far more than a technical debate about spectroscopic analysis. It embodies humanity's first genuine confrontation with the possibility that we are not alone in the universe. For centuries, philosophers, theologians, and scientists have speculated about the existence of extraterrestrial life. But these discussions remained largely theoretical until Webb's observations provided concrete data that could support such claims. The 99.7% confidence level reported by Professor Madhusudhan's team, while falling short of the gold standard required for scientific discovery, represents the closest humanity has ever come to detecting actual signs of life beyond Earth. This threshold moment forces us to grapple with questions that transcend pure science. What would the confirmation of alien life mean for human identity, purpose, and our understanding of consciousness itself? The philosophical implications of potential life on K2-18b become even more profound when we consider the nature of this distant world. Unlike the Earth-like planets that have dominated our imagination of alien life, K2-18b represents a completely foreign environment where any potential organisms would exist under conditions utterly unlike those that gave rise to terrestrial biology. The planet's thick hydrogen atmosphere, massive scale, and likely global ocean create an environment where life, if it exists, would have evolved along pathways completely independent of our own biological heritage. This possibility challenges one of the fundamental assumptions underlying much of astrobiology, that life elsewhere would necessarily resemble life as we know it on Earth. Carl Sagan once wrote that extraordinary claims require extraordinary evidence, but he also recognized that the discovery of extraterrestrial life would represent the end of humanity's cosmic loneliness. The potential biosignatures detected by Webb on K2-18b force us to confront this duality in real time, as the scientific community struggles to balance skepticism with the profound implications of a positive detection. Dr. Catherine Hayman's observation that even with perfect data, we can't say for sure that this is of a biological origin on an alien world because loads of strange things happen in the universe, highlights the inherent challenge of interpreting alien chemistry through the lens of terrestrial biology. This uncertainty reflects a deeper philosophical problem. Our understanding of life itself remains fundamentally limited by our single example of biology, making it difficult to recognize alien life that might operate through completely different biochemical principles. The direct imaging discoveries achieved by Webb, particularly the detection of TWA7b, represent a different but equally significant philosophical milestone. For the first time in human history, we possess actual photographs of worlds orbiting distant stars, transforming exoplanets from abstract statistical concepts into tangible realities that we can observe and study directly. This transformation from the theoretical to the visual carries profound psychological implications for how humanity relates to the cosmos. TWA-7b, floating in its debris disk 111 light-years from Earth, becomes not just a scientific discovery, but a concrete reminder of the vast community of worlds that populate our galaxy. The fact that this Saturn-mass planet is 10 times lighter than any previously imaged exoplanet demonstrates that our technological capabilities are rapidly approaching the threshold where we might directly observe potentially habitable worlds. The temporal dimension of Webb's discoveries adds another layer of philosophical complexity to our understanding of cosmic life. TWA-7b orbits a star that is only 6.4 million years old, making it an infant by cosmic standards. Yet the planet appears to be gravitationally sculpting its surrounding debris disk in ways that suggest substantial evolutionary development. This observation forces us to consider the timescales on which planetary systems develop and potentially give rise to life. If planets can form and achieve complex gravitational interactions within just a few million years of their star's birth, then the universe may be filled with worlds at various stages of development, some perhaps harboring life forms that evolved in environments we can barely imagine. The discovery of the tiny moon S2025U1 around Uranus provides a more subtle but equally important philosophical insight into the nature of cosmic discovery itself. This 6-mile diameter world remained completely invisible to NASA's Voyager 2 probe during its historic 1986 flyby, and eluded detection by subsequent observations until Webb's unprecedented sensitivity revealed its presence. The moon's discovery serves as a humbling reminder of how much remains hidden in our own solar system, despite decades of intensive exploration. If a moon orbiting one of our own planets can remain undetected until 2025, what other secrets might be concealed in the vast expanses between the stars? This realization encourages a sense of cosmic humility, acknowledging that our understanding of the universe remains fundamentally incomplete despite our rapidly advancing technological capabilities. The case of the potentially disappearing planet around Alpha Centauri A illustrates another profound aspect of cosmic discovery: the role of patience and persistence in revealing universal truths. The planet's intermittent visibility, appearing in August 2024, observations but absent during follow-up studies in February and April 2025, demonstrates how the universe reveals its secrets according to its own rhythms rather than human timelines. This discovery process reflects a deeper truth about scientific inquiry. Our understanding of the cosmos develops through sustained observation and analysis that often spans decades or even centuries. The fact that our nearest stellar neighbor may harbor a planet that appears and disappears according to the complex dynamics of binary star orbital mechanics reminds us that the universe operates on scales and through processes that dwarf human experience. Webb's discoveries also illuminate the fundamental interconnectedness of cosmic phenomena. The gravitational sculpting of debris disks by planetary companions, the complex atmospheric chemistry that might produce biosignatures on distant worlds, and the delicate orbital mechanics that govern planetary systems all demonstrate how individual cosmic objects exist within vast networks of physical relationships. This perspective encourages what astronomer Carl Sagan called a cosmic perspective, recognizing that Earth and humanity exist as integral parts of a universe characterized by profound physical and potentially biological interconnectedness. The technological achievements that enable Webb's observations represent their own form of philosophical statement about human capability and cosmic ambition. The telescope's 6.5-meter segmented mirror, operating at temperatures just above absolute zero, while floating in the gravitational balance between Earth and Sun, embodies humanity's determination to transcend the limitations of our terrestrial perspective. The precision required to detect molecular signatures in exoplanetary atmospheres across interstellar distances represents a triumph of human ingenuity that would have been inconceivable just decades ago. Yet these achievements also highlight our cosmic insignificance, demonstrating how much effort and resources are required to gather even basic information about our galactic neighbors. As Webb continues its mission, each new discovery contributes to a gradually emerging picture of a universe teeming with worlds and potentially life in forms we are only beginning to imagine. This evolving understanding challenges us to expand our conception of what it means to be human in a cosmic context, moving away from anthropocentric worldviews toward perspectives that acknowledge our membership in a vast community of potentially conscious beings scattered throughout the galaxy. Whether K2-18b ultimately proves to harbor life or represents an exotic example of abiotic chemistry, the philosophical journey initiated by Webb's discoveries has already transformed humanity's relationship with the cosmos, opening our eyes to possibilities that will shape human thought for generations to come. Let's move to our ninth part of the documentary, where we drift into the more contemplative and peaceful realms of cosmic discovery, exploring how Webb's revelations about distant worlds invite us to find solace and wonder in our expanding understanding of the universe. As we near the end of our journey through the telescope's extraordinary discoveries, it becomes appropriate to pause and reflect on the deeper emotional and spiritual dimensions of what we've learned, allowing the gentle rhythm of scientific wonder to carry us toward the tranquil shores of cosmic perspective. The discoveries we've explored tonight represent more than just technical achievements or data points in astronomical databases. They constitute profound moments of connection between human consciousness and the vast tapestry of worlds that populate our galaxy, each one a testament to the creative power of the universe itself. The story of TWA-7b, that Saturn mass world floating serenely within the debris disk of its young star, offers a particularly meditative lens through which to view our place in the cosmos. This distant planet, captured in humanity's first direct image of an exoplanet discovered by Webb, orbits its 6.4 million year old host star with a patience that spans geological ages. Located 111 light years from Earth, TWA-7b exists in a realm where time moves according to cosmic rhythms rather than human schedules, where the gravitational dance between planet and debris disk unfolds over millions of years, with a grace that transcends our everyday experience. The planet's role in sculpting the narrow rings within its stellar system demonstrates how individual worlds participate in the larger choreography of cosmic evolution, creating order and structure through the simple but profound action of gravity operating across vast expanses of space and time. The intermittent visibility of the potential planet around Alpha Centauri A provides another source of cosmic contemplation, reminding us that the universe reveals its secrets according to its own mysterious schedule rather than human expectations. The planet's appearance in August 2024, observations followed by its absence during February and April 2025, follow-up studies creates what researchers have dubbed the case of the disappearing planet, a phenomenon that highlights the patient persistence required for astronomical discovery. This cosmic hide-and-seek game reflects the elliptical nature of the planet's potential orbit, bringing it close enough to its host star during certain periods that Webb's instruments cannot distinguish it from Alpha Centauri A's overwhelming brightness. There is something profoundly peaceful about this celestial rhythm, the way a world might spend years hidden in its star's embrace before emerging once again into the darkness where telescopes can detect its presence. The discovery of the tiny moon, S2025U1, around Uranus carries its own quiet significance, demonstrating how much mystery remains even within our own solar system. This 6-mile diameter world, the 29th known moon of the ice giant, managed to remain completely invisible to NASA's Voyager 2 probe during its 1986 encounter, and eluded detection by subsequent observations until Webb's unprecedented sensitivity revealed its presence. The moon follows a nearly circular orbit, approximately 35,000 miles from Uranus's center, suggesting that it formed in its current location rather than being captured from elsewhere in the solar system. There is something deeply comforting about this discovery, the realization that new worlds can still be found even in our cosmic backyard, that the universe continues to surprise us with hidden treasures that await patient observation and technological advancement. Webb's atmospheric observations of K2-18b, regardless of the ultimate resolution of the biosignature controversy, represent humanity's most intimate glimpse into the chemical processes operating on a world that might harbor life. The detection of water vapor, methane, carbon dioxide, and potentially dimethyl sulfide in the planet's hydrogen-rich atmosphere creates a portrait of a world where complex chemistry unfolds in conditions utterly unlike those on Earth. Whether these chemical signatures ultimately prove to be the result of biological processes or exotic abiotic chemistry, they demonstrate the incredible diversity of environments that exist throughout our galaxy. each one representing a unique experiment in the fundamental forces that govern matter and energy across cosmic scales. The philosophical implications of Webb's discoveries invite us to embrace what Carl Sagan called the cosmic perspective, a worldview that recognizes our fundamental interconnectedness with the universe itself. Each photon of light captured by Webb's 6.5-meter mirror has traveled across interstellar distances for years, decades, or even centuries before being focused onto the telescope's sensitive infrared detectors. These ancient particles of light carry within them the chemical signatures of distant worlds, connecting us across space and time to planetary systems that existed long before human civilization began its journey toward technological capability. The molecules of dimethyl sulfide potentially detected in K2-18b's atmosphere, the thermal radiation from TWA-7b's warm surface, and the reflected starlight from the tiny moon around Uranus all become part of our expanding understanding of cosmic chemistry and planetary evolution. The technical achievements that enable Webb's discoveries also provide their own source of contemplation and wonder. The telescope's operation at temperatures just 50 Kelvin above absolute zero, maintained by its tennis court-sized sunshield while floating at the LBL2, Lagrange, 1.5 million kilometers from Earth, represents humanity's ability to create islands of extraordinary sensitivity in the vast ocean of space. The precision required to align Webb's 18 hexagonal mirror segments into a single, perfectly focused optical system demonstrates the remarkable capability of human engineering and scientific collaboration. These achievements remind us that while we remain confined to our small rocky planet, our consciousness and technological reach extend far beyond the bounds of Earth's atmosphere. The ongoing nature of Webb's mission, with enough fuel to continue operations for at least 2 decades, provides a source of comfort and anticipation for future discoveries. The telescope will continue its patient observations of distant worlds long after tonight's contemplation ends, gathering photons from alien atmospheres and debris disks with the same meticulous precision, whether humanity is watching or sleeping. This constancy of scientific observation creates a bridge between our momentary awareness and the eternal processes that govern cosmic evolution, allowing us to participate in a conversation with the universe that transcends individual human lifespans. The uncertainty surrounding K2-18b's potential biosignatures also offers its own form of peaceful reflection. Rather than seeing the scientific debate as a source of frustration or disappointment, we can view it as evidence of the universe's profound complexity and our own intellectual humility in the face of cosmic mystery. The 3 sigma confidence level reported by Professor Madhusudhan's team represents not just a statistical threshold, but a moment of genuine uncertainty where human knowledge encounters the edge of the known. This liminal space between discovery and skepticism reflects the ongoing nature of scientific inquiry, where each answer generates new questions and every observation reveals new layers of complexity in the cosmic systems we seek to understand. As we prepare to conclude our journey through Webb's remarkable discoveries, we can take comfort in knowing that the telescope continues its work even as we drift toward sleep, patiently collecting light from distant worlds and adding to humanity's slowly expanding understanding of our place in the cosmic community. Whether K2-18b ultimately proves to harbor life, whether the Alpha Centauri planet emerges from its stellar hiding place, and whether TWA-7b reveals new secrets about planetary formation. The universe continues its patient work of revelation, offering endless opportunities for wonder, discovery, and the quiet satisfaction of expanding human knowledge about the infinite diversity of worlds that populate the galaxy we call home. Let's move to our 10th part of the documentary, where we gather the threads of Webb's revolutionary discoveries into a gentle tapestry of cosmic understanding and prepare to drift into the peaceful realm of sleep, carried by the rhythm of scientific wonder and the comforting knowledge that the universe continues its patient work of revelation while we rest. As our journey through the telescope's extraordinary achievements draws to a close, we find ourselves transformed by the experience of witnessing humanity's expanding view of the cosmos. From the controversial potential biosignatures on K2-18b to the direct imaging of distant worlds, each discovery adding another note to the symphony of cosmic awareness that now accompanies us towards sleep. The recent discovery of the tiny moon S 2025 U1 orbiting Uranus serves as a perfect metaphor for the hidden wonders that surround us even in familiar territories. This 6-mile diameter world managed to remain completely invisible to NASA's Voyager 2 probe during its historic 1986 flyby, and eluded detection by subsequent observations until Webb's unprecedented sensitivity revealed its presence just 10 months ago. The moon's discovery required 10 separate 40-minute exposures using Webb's near-infrared camera, each image captured during the quiet hours when Earth had rotated away from the chaos of human activity, allowing the telescope to peer into the serene darkness where this tiny world had been patiently orbiting for billions of years. There is something profoundly comforting about this discovery, a reminder that mysteries persist even within our own cosmic neighborhood, waiting for the right combination of technology, patience, and human curiosity to bring them into the light. Dr. Mariame El-Mutamid, who led the team that discovered S 2025 U1, described finding a small moon, something that NASA's Voyager 2 couldn't see during its flyby nearly 40 years ago. Her words capture the essence of progressive discovery, the way each generation of instruments and observers builds upon the work of previous explorers, revealing details that were always present but beyond the reach of earlier technology. The moon orbits approximately 35,000 miles from Uranus's center in an almost perfectly circular path, suggesting that it formed in its current location rather than being captured from elsewhere in the solar system. This formation scenario implies that even the outer reaches of our solar system once possessed the kind of debris disks we now observe around young stars like TWA7, providing the raw material for moon formation through processes that operated billions of years ago but left their signatures in the orbital mechanics we can observe today. The discovery of S 2025 U1 also illustrates Webb's remarkable ability to detect incredibly faint objects even when they orbit close to much brighter sources. The moon exists within the complex gravitational environment of Uranus's ring system, where the scattered light from countless particles of dust and ice creates a challenging observational environment for detecting small satellites. Yet Webb's sophisticated instruments, originally designed to detect the faintest galaxies at the edge of the observable universe, prove equally capable of revealing tiny worlds hiding in the glare of their parent planet's reflected sunlight. This versatility demonstrates how the pursuit of cosmic extremes often leads to unexpected capabilities closer to home, a principle that has guided astronomical instrument development for generations. The philosophical implications of discovering new moons around planets that were supposedly well explored extends beyond simple inventory taking to touch on deeper questions about the nature of discovery itself. Uranus has been observed through telescopes for over 2 centuries since William Herschel first noticed its disk-like appearance in 1781. Yet it continued to harbor secrets that remained invisible until 2025. This timeline reminds us that even within our own solar system, our knowledge remains incomplete, encouraging a sense of cosmic humility that acknowledges how much remains to be discovered about the universe we inhabit. If a moon can orbit one of our own planets for billions of years without human detection, what other secrets might be concealed in the vast expanses between the stars, waiting for future generations of instruments and observers to reveal them? The context of Webb's broader discoveries provides an even richer source of contemplation as we prepare for sleep. The telescope's detection of potential biosignatures on K2-18b, whether ultimately confirmed or refuted, represents humanity's closest approach yet to answering the fundamental question of whether we are alone in the universe. The scientific debate surrounding Professor Madhusudhan's findings reflects the careful, methodical process through which human knowledge expands. Where extraordinary claims require extraordinary evidence, and every detection must withstand the scrutiny of independent verification. This process, while sometimes frustrating in its deliberate pace, provides a source of confidence that our understanding of the cosmos develops through rigorous inquiry rather than wishful thinking. The direct imaging of TWA-7b, floating serenely in its debris disk 111 light-years from Earth, offers another touchstone for peaceful reflection on our place in the cosmic community. This Saturn mass world represents our first direct photograph of a planet discovered by Webb, transforming exoplanets from abstract statistical concepts into visual realities that we can observe and contemplate. The planet's role in gravitationally sculpting its surrounding debris disk demonstrates how individual worlds participate in the larger choreography of cosmic evolution, creating order and structure through the patient application of physical forces operating across millions of years. There is something deeply satisfying about this process, the way gravity and orbital mechanics work together to create the beautiful ring structures that Webb's instruments can now observe in exquisite detail. The intermittent visibility of the potential planet around Alpha Centauri A adds its own note of cosmic mystery to our contemplation. The world's appearance in August 2024 observations, followed by its absence during follow-up studies, creates what researchers have dubbed the case of the disappearing planet, a phenomenon that reflects the elliptical nature of the planet's potential orbit around our nearest stellar neighbor. This cosmic hide-and-seek game operates according to timescales that dwarf human experience, where a planet might spend months or years hidden in its star's glare before emerging once again into the darkness where telescopes can detect its presence. The patience required to track such phenomena across multiple observing seasons reflects the broader rhythm of astronomical discovery, where definitive answers often emerge only through sustained observation and analysis spanning years or even decades. As we prepare to conclude our journey through Webb's discoveries, we can take comfort in knowing that the telescope continues its work while we sleep, patiently collecting photons from distant worlds and adding to humanity's expanding database of cosmic knowledge. The observatory operates according to a carefully planned schedule of observations that spans months and years into the future, ensuring that important targets like K2-18b, TWA-7, and Alpha Centauri A will receive continued scrutiny as Webb's mission progresses. This constancy of scientific observation creates a bridge between our momentary awareness and the eternal processes that govern cosmic evolution, allowing us to participate in a conversation with the universe that transcends individual human lifespans. The discoveries we have explored tonight represent just the beginning of Webb's transformative impact on our understanding of planetary systems and the potential for life beyond Earth. With enough fuel to operate for at least 2 decades, the telescope will continue revealing new worlds, new atmospheric compositions, and new insights into the incredible diversity of planetary environments that populate our galaxy. Whether K2-18b ultimately proves to harbor life, whether the Alpha Centauri planet emerges from its stellar hiding place, and whether TWA-7b reveals new secrets about planetary formation, the universe continues its patient work of revelation, offering endless opportunities for wonder, discovery, and the quiet satisfaction that comes from expanding human knowledge about our place in the infinite cosmos that surrounds us all. Let's move to our last part of the documentary, where we gather all the threads of Webb's remarkable discoveries into a final meditation on humanity's expanding cosmic perspective and prepare to drift peacefully into sleep, carried by the gentle rhythm of scientific wonder and the profound comfort that comes from knowing our place in an infinite universe filled with worlds, moons, and possibilities beyond our wildest imagination. As we reach the conclusion of our journey through the telescope's extraordinary achievements, we find ourselves forever changed by the experience of witnessing humanity's greatest technological triumph, gradually unveiling the secrets of distant worlds, from the controversial potential biosignatures on K2-18b to the serene discovery of tiny moons in our own cosmic backyard. The story of S2025 U1, the newly discovered moon of Uranus, provides a perfect metaphor for the hidden wonders that surround us, even in seemingly familiar territories of our solar system. This 6-mile diameter world had been orbiting Uranus for billions of years, completing its 35,000-mile circuit around the ice giant with patient regularity while remaining completely invisible to human observation until Webb's unprecedented sensitivity revealed its presence in 10 separate 40-minute exposures captured by the telescope's near-infrared camera. Dr. Maryam El-Mutamid from the Southwest Research Institute, who led the discovery team, described finding a small moon, something that NASA's Voyager 2 couldn't see during its flyby nearly 40 years ago, highlighting how each generation of astronomical instruments builds upon the work of previous explorers while revealing details that were always present but beyond the reach of earlier technology. The moon now joins a family of 29 satellites orbiting Uranus, nestled between the planet's main ring system and its collection of larger, more famous moons, serving as a reminder that even within our own solar system, mysteries persist and new discoveries await patient observers equipped with sufficiently sensitive instruments. The philosophical implications of discovering S2025 U1 extend far beyond simple inventory taking to touch on deeper questions about the nature of discovery and our evolving relationship with the cosmos. Uranus has been observed through telescopes for over 2 centuries since William Herschel first noticed its disk-like appearance in 1781, yet it continued to harbor this secret moon that remained invisible until 2025. This timeline encourages a sense of cosmic humility, acknowledging that even within our own planetary neighborhood, our knowledge remains fundamentally incomplete despite decades of intensive exploration with increasingly sophisticated instruments. The Moon's location close to Uranus's ring system suggests that it may play a role in sculpting the planet's distinctive narrow rings through gravitational interactions, demonstrating how small worlds can have profound effects on the larger systems of which they are part. Webb's broader catalog of discoveries provides an even richer source of contemplation as we prepare for sleep. The telescope's detection of compelling evidence for the Saturn mass planet KTWA-18b, floating serenely within its debris disk 111 light-years from Earth, represents our first direct photograph of a world discovered by Webb, transforming exoplanets from abstract statistical concepts into visual realities that we can observe and study. The planet's role in gravitationally sculpting its surrounding debris disk demonstrates the patient work of cosmic evolution, where individual worlds participate in the larger choreography of stellar system formation through the simple but profound application of gravity operating across millions of years. There is something deeply satisfying about this process. The way physical forces work together over cosmic timescales to create the beautiful structures that Webb's instruments can now observe in unprecedented detail. The controversial potential biosignatures detected on K2-18b continue to represent humanity's closest approach yet to answering the fundamental question of whether we are alone in the universe, regardless of whether Professor Madhusudhan's findings ultimately prove correct. The 3 sigma confidence level of the dimethyl sulfide detection, while falling short of the 5 sigma standard typically required for claiming scientific discovery, has initiated a profound conversation about how we recognize and interpret signs of life in alien environments that bear no resemblance to Earth. The ongoing scientific debate surrounding these findings reflects the careful, methodical process through which human knowledge expands, where extraordinary claims require extraordinary evidence, and every detection must withstand the scrutiny of independent verification by multiple research teams using different analytical approaches. The intermittent visibility of the potential planet around Alpha Centauri A adds its own unique note of cosmic mystery to our final contemplation. The world's appearance in August 2024, observations, followed by its absence during February and April 2025, follow-up studies, creates what researchers have dubbed the case of the disappearing planet, a phenomenon that reflects the elliptical nature of the planet's potential orbit around our nearest stellar neighbor. This cosmic hide-and-seek game operates according to timescales that dwarf human experience, where a planet might spend months or years hidden in its star's glare before emerging once again into the darkness where telescopes can detect its presence. The patience required to track such phenomena across multiple observing seasons reflects the broader rhythm of astronomical discovery, where definitive answers often emerge only through sustained observation and analysis spanning years or even decades. Webb's technical achievements continue to inspire wonder as we consider the extraordinary engineering required to make these discoveries possible. The telescope's 6.5-meter segmented mirror, composed of 18 hexagonal, gold-coated beryllium segments operating at temperatures just 50 Kelvin above absolute zero, provides unprecedented infrared sensitivity while floating in the gravitational balance between Earth and Sun at the L2 Lagrange point 1.5 million kilometers from our planet. The precision required to align these mirror segments into a single, perfectly focused optical system while maintaining thermal stability in the harsh environment of space represents one of humanity's greatest technological achievements, demonstrating our species' remarkable ability to transcend the limitations of our terrestrial perspective through ingenuity, collaboration, and sustained effort across decades of development. The ongoing nature of Webb's mission provides perhaps the greatest source of comfort as we prepare to drift into sleep. With enough fuel to operate for at least 2 decades, the telescope will continue its patient observations of distant worlds long after tonight's contemplation ends, gathering photons from alien atmospheres and debris disks with the same meticulous precision, whether humanity is actively watching or peacefully sleeping. This constancy of scientific observation creates a bridge between our momentary awareness and the eternal processes that govern cosmic evolution, allowing us to participate in a conversation with the universe that transcends individual human lifespans and connects us to the larger story of cosmic discovery that began with our earliest ancestors gazing up at the night sky. The diversity of worlds revealed by Webb's observations suggests that the universe contains planetary environments spanning an incredible range of masses, compositions, and orbital configurations, many of which have no analogs in our own solar system. From the hydrogen-rich atmosphere of K2-18b to the debris disk environment of TWA7b, from the tiny ice and rock composition of S/2025U1 to the potential gas giant around Alpha Centauri A, each discovery expands our understanding of the creative possibilities inherent in cosmic evolution. These worlds exist as part of a vast community of planets that populate our galaxy, each one representing a unique experiment in the fundamental forces that govern matter and energy across cosmic scales. As we reach the end of our journey through Webb's extraordinary discoveries, we can rest peacefully, knowing that the telescope continues its work while we sleep, adding new chapters to humanity's expanding understanding of our place in the infinite cosmos that surrounds us. The universe continues its patient work of revelation, operating according to rhythms that span millions and billions of years, offering endless opportunities for wonder, discovery, and the quiet satisfaction that comes from knowing that we live in a cosmos filled with worlds beyond our imagination, each one a testament to the creative power of the universe itself. Whether tomorrow brings confirmation of life on K2-18b, the reappearance of the Alpha Centauri planet, or entirely new discoveries that we cannot yet anticipate, the cosmos continues its eternal dance of creation and evolution, inviting us to participate as conscious observers in the greatest story ever told, the story of the universe coming to know itself through the curious eyes of humanity and our remarkable machines that peer into the darkness and bring back light.